In this video, we're finally ready to talk about the law of conservation of energy. So at this point, you've learned about work, you've learned about conservative forces and how conservative forces and their energies are conserved. In other words, mechanical energy is conserved when dealing with conservative forces. And you've also learned now about non-conservative forces and how non-conservative forces have the ability to do work on or against a system, thereby changing the energy within a defined system. So we can state that energy in an isolated system is conserved. So let's take a look at our mechanical energies again. We have kinetic energy and we have our potential energies, which could include spring potential energy, also referred to as elastic potential energy, and of course, gravitational potential energy. So let's take a look at this video clip from a PhET simulation. As you can see, this skateboarder is going back and forth up and down a ramp. Now look at the bar graph on the far left side. You can see the green bar represents kinetic energy, blue bar represents gravitational potential energy, and the beige bar on the far right represents the total mechanical energy. Please notice that as this skateboarder goes back and forth, kinetic energy is converted into potential energy and then potential back into kinetic. However, the overall total mechanical energy within this skateboarder Earth system is conserved. In other words, it remains constant. Now, what I'm going to do is expand this out to include all of our potential energy and our kinetic energy, initial on the left side, final on the right side. And we'll do this for every scenario. This equation is not on your equation sheet. I've already shown you the relevant equations from your equation sheet. So you need to be able to look at a given scenario, define your system, identify any non-conservative forces that may be at work, and go from there. In this case here, we have no friction. You can see the red bar on the graph, it reads 0. So there is no friction. In other words, no conservative forces are currently at work. So if we look at what we could potentially have initially in this video clip, we could have an initial velocity because the skateboarder is moving back and forth. We could have a potential gravitational potential energy, depending on our defined 0 line. There's no springs associated with this scenario whatsoever. So depending on where we start the scenario, we may or may not have kinetic energy, gravitational potential energy initial, and also we may or may not have kinetic energy final or gravitational potential energy final. Let's do an example so this can hopefully make a little more sense here. So looking at the same clip here, you're asked to calculate the total energy in the skateboarder Earth system. So at any given point, watch these bar graphs as they go back and forth. There's two areas where you could really determine easily the total energy in this system. And that would be when the skateboarder is at the very top of a ramp, which is 6 meters above the ground, or it could be the skateboarder's kinetic energy when he or she's at the bottom of the ramp, has the greatest kinetic energy, or it could be somewhere in between. But we want to be smart about how we approach this. So let's come up with a plan. Let's find the gravitational potential energy at the top of the ramp. And that is the total energy in the system. So let's once again expand out our mechanical energies. Let's go ahead and acknowledge we have no work done by a non-conservative force. In other words, we are dealing with a frictionless scenario. At the top of the ramp is the skateboarder moving. At the very top, no, there's no kinetic energy. At that instant, the skateboarder stops. Is there gravitational potential energy relative to a defined 0 line? Sure. Let's go ahead and place the 0 line at the bottom of the ramp. Then, of course, we do not have any springs or any elastic material at all in this scenario, or in this video for that matter. But I'm including it in the overall equation so that you understand that it could be a part of the mechanical energy of the system. Let's look at our final scenarios. At the bottom of the ramp, is the skateboarder moving? Yes, in fact, the skateboarder has its greatest kinetic energy. Look at the bar graphs. Therefore, the skateboarder has the greatest overall speed. Is there gravitational potential energy? No. We're going to put the 0 line down at the bottom of that ramp. There's no more gravitational potential energy. That leaves us with this scenario here, that the total energy for this system is really just the mass times the acceleration due to gravity times the height above the 0 line, or 6 meters. That's going to give us the total energy. Now, if you're looking over here and wondering, what about that? Remember, I said that. We could also find the kinetic energy at the bottom of the ramp, and that too would also be the total energy. Take a look at these bar graphs once again to see that. So the mass of this skateboarder, including the skateboard, is 60 kilograms. So given that information, we can simply plug in these values and calculate our energy total. And again, that's the total mechanical energy is 3,600 joules. Now let's go ahead and consider the skateboarder's maximum speed, which, as I just alluded to, would be at the bottom of the ramp. So coming up with a plan, we're going to solve for the speed of this skateboarder at the bottom of the ramp, because that's going to be the maximum kinetic energy. Again, reference the bar graphs. Watch them as they go back and forth. So we have the initial potential energy, which was the total energy, which is still 3,600 joules. And we're going to set that equal to 1/2 mv squared, or the final kinetic energy for when the skateboarder is at, again, the bottom of the ramp. At that point, look at the bar graphs, all of the potential energy is converted into kinetic energy. However, total energy is conserved within this system. So what we can do here, if we want, is we can say, oh, mass doesn't matter, cancel out mass, and we can solve for V final, and it's very simple. So if we take the square root of this quantity, we find out the skateboarder is going 11 meters per second at the bottom of the ramp. Take a look at the speedometer as the skateboarder goes back and forth. It's right around 11 meters per second. Now, there's another way. It's really all the same. Remember, we already determined the total energy in the system, and we're saying all of that energy is being converted into kinetic energy. So we could also just say 3,600 joules equals kinetic energy final. We could take these values algebraically, solve for V final, and we get the exact same answer of 11 meters per second in this scenario. Now, let's go ahead and find the speed of the skateboarder 3 meters below the top of the track. This is really cool because using the law of conservation of energy, we can find the skateboarder's speed anywhere up and down the track. 1 meter above the bottom, 2 meters below the top, it wouldn't matter. We could easily find it as long as we set up our energy equations correctly. So let's go ahead and again, take our total mechanical energy initial. Let's start at the top of the ramp. Skateboarder's not moving, there's no spring, and we still have no friction. Now let's look at what's happening 3 meters below the top of the ramp. Is the skateboarder moving? Absolutely. Is the skateboarder above our zero line that we placed at the bottom of the ramp? Sure. So we're left with the following energy expression. So now all we need to do is fill in values. So we could look at our total energy, which we've calculated to be 3,600 joules. That didn't change. And we can now subtract MGH final from both sides. If you're wondering where this all of a sudden ended up on the left side, it's because I'm isolating to solve for V final. Algebraically, we're solving for the final velocity. And our final velocity in this scenario, we've defined as 3 meters below the top of the track. I also want to show you, if you were to plug in values, mass cancels out throughout this entire expression. However, we've already calculated the total energy, so we can use that as well. Either one of these will work out. You'll get the same answer as I showed you several minutes ago. So here we take our 3,600 joules, we subtract our potential gravitational energy final. So we take the mass of 60 kilograms times little g times 3 meters. That's 3 meters above the zero line, or 3 meters below the top, and we set that equal to the kinetic energy final. Now we make a prediction. Is this going to be greater or less than 11 meters per second? Oh, it's going to be less than, obviously. Because the skateboarder is halfway down the ramp, I wonder if the velocity will be exactly 1/2 of 11 meters per second. I wonder if the velocity will be 5.5 meters per second. Let's find out here. So we have 1,800 joules, that's the left side, 3,600 minus the 1,800 is equal to 1/2 mv squared. Algebraically, solving for velocity final, we get an answer of 7.7 meters per second. That's not exactly half. Why? Well, let's look at our proportionalities. This is a non-linear relationship. So because the height, when compared to when the skateboarder went 6 meters all the way to the bottom and reached a speed of 11 meters per second, because the height is half of that, we want to take and put the square root of 0.5. Well, what is that? Well, that's equal to 0.707, which means that our speed is going to be that much less. So if we take this value here and multiply it by 11, guess what? We get about 7.7 meters per second, because the overall speed is a little over 7/10 of what it would have been at the bottom. This is a nonlinear, this is an exponential relationship. Now look at this new video clip. Let's calculate the speed of the skateboarder at the top of this small hill. Take a moment, look at the bar graphs, note the total mechanical energy is constant, note there are no non-conservative forces, so we're dealing with a situation in which we could potentially have kinetic energy or gravitational potential energy. There's no spring, there's no friction, and so we're left with this possibility. Now here is where we want to think about where we can place that zero line that makes the most sense. So if we choose to place the zero line here, we see the yellow zero line means at the top of the small hill, the skateboarder has zero gravitational potential energy. That's going to simplify our calculations. So essentially all we're doing is going from here to here. And remember, because we're dealing with conservative forces, in other words, the force, the gravitational potential energy, the force of gravity, we're dealing with an independent path. It doesn't matter the path taken. It doesn't matter if the skateboarder went through a loop-de-loop. All that matters is our height initial here and our height final. That's it. Look how easy this becomes. We're only solving for our gravitational potential energy and setting it equal to our kinetic energy, and algebraically we're going to find V final in this scenario. Note also that I could have easily done this. Mass isn't even a factor, it completely cancels out. We're left with 1,800 joules on the left side, and we're algebraically, if we multiply both sides by 2, take the square root and divide by 60 kilograms, we find our speed to be, once again, 7.7 meters per second, which makes sense because the skateboarder's change in height for this system with no friction was, again, 3 meters. So if we look now at this scenario, I want you to watch it carefully. Look at the total energy. Guys, work is being done by a non-conservative force to our isolated system. So work is being done against the skateboarder Earth system. This is resulting in a change in the total mechanical energy of the skateboarder Earth system. Notice eventually this skateboarder comes to a complete stop due to the force of friction acting upon the system. And guys, we've finished now talking about the law of conservation of energy and applying these concepts to a system. And I'll see you guys in class.